We will take a short digression and give a quick recap of power series on real line. Now, you must have seen power series in your complex analysis course, which you are going through right now, but you may not have seen power series in your real analysis sequence. I'm not sure whether you have seen it or not. But it's anyway good to at least state the results that we will need. And why we need it will become clear today itself. Okay, so suppose you have a sequence indexed by n bigger than or equal to 0 of real numbers. For such a sequence, a power series around 0 is just a formal expression of the form summation an s power n as n runs over non-negative integers. It's just an expression a0 plus a1s plus a2s square plus a3s cube and so on. Okay? So a priori, it's just a formal expression. Now define R to be 1 over lim sup as n goes to infinity of an power 1 over n. Now, of course, you have to use the convention. There is this limit, this lim sup may be 0. If it is 0, then we'll define R to be infinity. On the other hand, if this lim sup is infinite, then we'll define R to be 0. Okay? So we are using the conventions that 1 over 0 is infinity and 1 over infinity is 0. Now this R is called the radius of convergence for this power series. It can be shown that this series actually converges, in fact absolutely, whenever mod s is less than R. On the other hand, it diverges whenever mod s is bigger than R. Now this just follows from root test, as simple as that. Now in complex analysis, you must have seen the same thing, except that the absolute value would be replaced by the modulus. The same thing here, okay? Now anyway, what can be actually shown is that in any interval, in any closed and bounded interval from minus R to R, okay, any closed and bounded interval which is strictly contained in open minus R to R, this convergence is actually uniform. Okay, it can be shown that. Anyway, it's not going to be so important. This R is called the radius of convergence. So because you know that it's going to converge inside R, inside this radius of R, radius in the sense radius around 0 on real line. And then outside, it's definitely going to diverge. Nothing can be said in general about what happens at s equal to R and s equal to minus R. Now, one thing we can observe easily is that if all the ANs are between 0 and 1, then, of course, this lim sup is less than or equal to 1. It can be 0, but it's definitely less than or equal to 1. Okay? And therefore, 1 over this lim sup is bigger than or equal to 1. Of course, it can be infinity also. If this is 0, this lim sup is 0, then R is infinity. But anyway, infinity is definitely bigger than or equal to 1. So therefore, the radius of convergence is going to be bigger than or equal to 1 whenever all the ANs are between 0 and 1. This will be crucially used today. Now anyway, since this converges in this interval, this defines a function on this interval. It's a function from minus R to R taking values in real lines. For each s in this interval, this is giving a real number. So therefore, you're getting a function. And this function actually is a continuous function. It can be shown that this is a continuous function. The fact that this is continuous is going to be important for us today as well. That's why I'm stating this. Now, what happens at the boundaries? Does it converge at the boundary or not is a question. And here is a theorem that relates to this question. Now, suppose your radius of convergence is strictly positive and strictly less than infinity. Now, of course, this defines a function on the interval minus r to r, which is a proper subset of real line, proper non-empty subset of real line, because r is strictly between 0 and infinity. Now then you can say the following. Say you look at the right endpoint, r. If this converges at s equal to r, if this power series converges as s equal to r, then this limit of as s approaches r from the left side exists and it equals this sum. By the way, this is called Abel's limit theorem. Okay? So in other words, if at the boundary the power series makes sense, then the function can be continuously extended to the boundary. On the other hand, if ans are all non-negative, then you can say if this is divergent, then this limit, the same limit of as, would actually be infinity. Well, of course, it will still equal this series, except that the series is divergent, so therefore this series sum is going to give you infinity. So we are going to use both statements of Abel's limit theorem in this course. Today we'll use the first part. Okay, now we'll define two power series. So for two states I and j, we define the power series Pij and Fij as follows. So Pij is the power series corresponding to the sequence Pijn, and Fij is the power series corresponding to the sequence Fijn. Now note that since both are probabilities, they are between 0 and 1. They may not be strictly between 0 and 1, but they're always between 0 and 1. And therefore, because of our observation, the radius of convergence is bigger than or equal to 1. It can be infinity, but it's bigger than or equal to 1. And hence, in the interval -1 to 1, this is a well-defined function. So Pijs and Fijs are well-defined, okay, on this open interval. One more observation is that if starting from I, the first hitting time of j is finite with probability 1, then Fijs is actually the probability generating function of this random variable first return time to j, first hitting time of j under Pi. Now this will be the case when the state j will be recurrent, for example. If j is recurrent, then starting from I, you hit j in a finite time has probability 1. So then this is a probability generating function. On the other hand, Pij is not a probability generating function because these guys never sum up to 1. Well, they may be sum up to 1, but in rare cases, not in general. But it is just the generating function for this sequence, Pijn. Okay, so we have these two power series, which are the two generating functions for the sequences Pijn and Fijn respectively. And we only care about the interval -1 to 1. Even though the actual radius of convergence can be strictly bigger than 1, but we only care about this range, this part of the generating function. Now note that if I is not equal to j, then Pijn is this sum for every n bigger than or equal to 0. Now if you translate this expression into the power series, then what you'll immediately get is that Pijs is equal to Fijs times Pjs. Why is it so? This is because if you look at the coefficient of s power n in this power series, is precisely this quantity. Okay, if you take the product and then compute the coefficient of S power n in the right-hand side, this is precisely this quantity, which is equal to the coefficient of S power n on the left-hand side, and therefore the two power series are the same. Now, of course, question is what happens when I is equal to J? And we will see that something different will happen when I is equal to J.